we are going to discuss about the construction of reflex fuzzy min-max neural network, which makes use of the compensatory neurons. So, in the last class we have said or we have seen that how to construct a fuzzy min-max neural network, where there is no concept of the reflex mechanism, or there is no concept of compensation to the membership functions computed by the different nodes or the different neurons which represent the different hyperboxes. So, I will take the same example. As in that example we had two cases, one of the overlap of hyperboxes and one of the containment of hyperboxes belonging to different classes, and see that without modifying the min max points of the classifying neurons, how we can add the different types of compensation neurons to have a reflex fuzzy min max neural network. So, I will take the same example that we have taken in the last class, that is, we had taken a set of points as given over here. So, if I take the first point, that is 0.7.7. So, 0.7.7 as we said comes somewhere over here, that is this point. Okay. So, whenever we have this training sample or training feature vector, as we said that we construct a neural network, or we construct one neuron in the middle layer of our fuzzy min max neural network. As we said that we have the number of input nodes and the number of output nodes which are fixed. So, as we are considering two dimensional feature vectors, so number of nodes in the input layer will be 2, and as we are considering just two classes C1, C2. So, number of nodes in the output layer will also be fixed. So, earlier what we tried to say is we tried to construct three matrices, one matrix U, the other matrix V, and the third matrix W, okay, where U matrix represents the connection from the middle layer neurons to the output layer neurons, and V matrix and W matrix, they represent the min max points of the hyperboxes represented by different neurons. So, as we said that each of these matrices will have two rows, and the entries in the matrices will be made while the neural network is trained. Okay. So, once I get this first training sample, this represents a point hyperbox for which the min point and max point will be the same, and as we know that this point belongs to class 1. So, in the U matrix I will make an entry 1 0, indicating that this neuron is connected to the output layer neuron representing class C1. Okay. And the min points and max points will be same as this feature vector, that is 0.7.7. So, we put 0.7 over here and 0.7 over here, here also we put 0.7, here also we put 0.7. And then when we take the second point, that is 0.75, which also belongs to the same class 1. So, in this hyperbox configuration, it will come over here, and I can expand the previous hyperbox to include this point. So, I get a hyperbox something like this, and as we said that as we are not creating any new hyperbox, so there is no neuron added in the middle layer. Okay. And as such the U matrix will remain the same. Okay. Now, what I have to change is the min point and the max point. Okay. So, you find that the min point that remains the same as 0.7.7, whereas the new max point becomes 0.75. So, I make the corresponding change in matrix W representing the max point. Then I take the third point training sample, which is 0.9.9, and this training sample belongs to class 2. Okay. So, obviously, I have to make a new hyperbox, and over here it will be again a point hyperbox representing 0.9, and that will be somewhere over here. And because this belongs to class C2, so I have to make a new neuron in the middle layer, and as this neuron belongs to class C2, so I will have a connection from here to here, where this output layer neuron represents class C2. Accordingly, in the mu matrix, I will have the entry 0, 1. Okay. The min point and max point of this new hyperbox, because it is a point hyperbox, again it will be 0.9 and 0.9. Here also it is 0.9 and 0.9. Okay. So, then I take the next point, which is 0.8, and this also belongs to class C2. So, I take this next point, which comes here, 0.8, what is that one? Yeah, this point, and assuming that this can be expanded to include this point, I expand this hyperbox to include this point. Okay. Accordingly, there will not be any change in the middle layer neuron, and there will not be any change in the U matrix, but the min point and max point they have to change, and over here the max point remains the same, that is 0.9, and the min point that becomes 0.8. Okay. So, I change the min point to 0.8 and 0.8. Okay. And then I take the other point, that is 0.1. So, enter in this is 0.1. Okay. And here, as this cannot be included within the first one, because this also belongs to class C1, this also belongs to class C1, but I cannot expand this to include this point. So, I have to enter a new node in the middle layer, and this node belongs to class C1. So, accordingly, I have to enter in the U matrix 1, 0. Okay. And the new entry in the min point and max points will be 0, 1, 0, 1. Okay. Similarly, here it is 0, 1, 0, 1. Then come to the next point, which is 0.2, again belonging to the same class C1. So, 0.2 is over here. I can expand this point hyperbox to include this 0.2. So, I am not adding any new hyperbox. So, accordingly, there will not be any change or any node added in the middle layer, and there will not be any change in the U matrix. However, the min point and max point of the previous hyperbox which has been expanded, that will change, and here the max point will be 0.2, 0.2. Okay. Then take the next point, which belongs to class C2, and the vector is 0.3. Okay. So, I take this 0.3, which is over here, and this belongs to class C2. So, I have to add a new neuron in the middle layer. So, I have to add a neuron over here, and this belongs to class C2. So, I have to change, I have to make an entry in the U matrix, which is 0, 1, and for this one I have to enter the min point and max point, and this being a point hyperbox, both of them will be 0.3 and 0.3. then I consider the next one, which is 0.15 belonging to the same class C2. So, you enter 0.15. Okay. Expand this point hyperbox to include this point 0.15. Okay. So, when I expand this, what I have to do is, because I am not adding any new node. So, in the middle layer the structure will remain the same. In matrix U I do not have to make any more entry, only the min point and max point of these two will be different. So, the min point, new min point of the previous hyperbox will be 0.15 and here it is 0.15. And now there will be a difference between the previous neural network that we were constructing and this new neural network that we are making, because in this case you find that there is an overlap. Okay. I have a overlap in this particular region. So, what I have to do is, in the compensatory section I have to add a new neuron which represents a hyperbox of this overlapped region. Okay. So, I will add a new neuron in the compensation section or in the reflex section. So, I will put over here in the overlap compensation section, I will add a new neuron. Okay. And in the overlap compensation section also I will have two output layer nodes, one corresponding to class C1, other one corresponding to class C2. Okay. And the function of this overlap compensation neuron will be to calculate what is the amount of compensation that has to be provided while calculating the membership function, and that compensation has to be added to the outputs of the neurons as given in the classification section. Okay. So, it has to give compensation to both C1 and C2. Okay. So, it has to give compensation to this class, also it has to give compensation to this class. So, this is an output layer neuron in the reflex section corresponding to class C1, and this is the output layer neuron in the reflex section corresponding to class C2. Okay. However, so accordingly, as we have proposed a matrix U over here, let us assume that for this overlap compensation section I have another matrix say Y. Okay. And in this matrix Y, because this neuron is feeding the output to both class C1 and C2, so both of them will be made equal to high. Okay. However, if I have three classes, three such classes, one of the class will be equal to 0, because every node in the middle layer in the compensation section or overlap compensation section provides compensation only to two classes corresponding to the two hyperboxes belonging to two classes which overlap. So, every neuron in the middle layer of the overlap compensation section will be connected to two output layer neurons in the overlap compensation section. Okay. So, here it is this Y matrix will be 1 1, and the min point and max point of this particular hyperbox will be the min max point of this region. Okay. So, here you find that the max point is given by 0.2 and min point is given by 0.15. Okay. So, accordingly, pardon? More than two hyperboxes overlapping in the same region is unlikely, because whenever by expansion a hyperbox gets overlapped with another hyperbox, the same hyperbox will not be expanded anymore. Okay. However, even then if there is such a possibility, then I will have pairwise compensation, class 1, class 2, class 1, class 3, class 2, class 3, like that. Okay. But it is quite unlikely, because once a hyperbox overlaps, the same hyperbox will not be expanded further. Okay. So, here the min point is 0.15 and the max point is 0.2, 0.2. So, corresponding to this particular neuron, I will enter in V matrix and W matrix the min point and max point as 0.15, 0.15, and here it will be the max point will be 0.12, 0.2 and 0.2. Okay. So, these are the mean point and max point of the hyperbox or the node in the overlap compensation region. Okay. But you notice that unlike in the previous case where we had broken these two hyperboxes to avoid such overlap, and accordingly these min max points are changed. But here we are not disturbing the hyperboxes which are already created in the classification section. So, that ensures that the points which are already learned, that knowledge which is already acquired, this knowledge will not be disturbed. Okay. And after that, again when I next take the next point, that is 0.45, 0.45, which belongs to class 1. So, 0.45, 0.45 that will come somewhere over here, and this belongs to class 1. Again for this I have to enter one node in the classification section, and this node belongs to class C1. So, I have to make in the U matrix an entry which is 1 0. Okay. And min point and max point of that is 0.45, 0.45, max point will also be 0.45 and 0.45. Okay. Then I take the next point, which is 0.5, 0.5, that is this one, put over here. The previous one is 0.45, 0.45. So, 0.45, 0.45 is somewhere here. Okay. 0.5, 0.5, that point comes over here. So, I have this hyperbox, and I do not have to add any node because the node is already added. So, accordingly I will not have any modification in the U matrix, but V and W matrices will be changed, okay, where the mean point remains the same, but the max point now becomes 0.5 and 0.5. Okay. Then I take the next point, which is 0.42, 0.42, that will come somewhere over here. Okay. This belongs to class C2. So, for this I have to add one more node, does not matter if I put on this side. Okay. And for this the min point and max point will be 0.42, 0.42, and because new node is added, so I have to make an entry in the matrix U, and this belongs to class C2. So, the entry in matrix U will be 0, 1, okay. And for this my min point and max points will be 0.42, 0.42, 0.42, 0.42. Okay. Then I take the next point, which is 0.55, 0.55, put in this 0.55, 0.55, this is 0.5, right? Yeah, this was 0.5. So, 0.55, 0.55 comes over here. Okay. I expand the previous hyperbox. Okay. So, accordingly, because it is expansion of the previous hyperbox, so I do not have to make any entry in the middle layer of the classification section. So, the classification section neurons remain the same, U matrix also remains the same, but the change I have to make is in the max point of this new neuron that has been added. Okay. So, when I change this max point, it becomes instead of 0.42, 0.42, it becomes 0.55, 0.55. But while doing so, you find that I have a containment. Okay. So, because there is a containment, I have to put one compensation neuron in the containment compensation section. So, I have one more section, that is containment compensation. Here again I will have two neurons in the output layer corresponding to class C1 and corresponding to class C2. I have to add one compensation neuron, containment compensation neuron. Okay. So, and this containment compensation neuron will give the compensation output to one of the classes, not to both. Okay. So, it will compensate the membership function of the class which contains the hyperbox of the other class, right. So, accordingly, the output of this neuron will be connected to class C2, it will not be connected to class C1, because the membership function of class C1 is not to be compensated. However, the membership function of class C2 is to be compensated. Okay. So, accordingly, I have to have a connection. Pardon? Container should be compensated. Yeah, container has to be compensated, not the one which is contained. Okay. So, because here it is hyperbox belonging to class C2, so the output of this neuron will be fed to the classifying neuron C2 in the containment compensation section. Okay. And to have this connectivity, let us put that we will maintain another matrix which is Z matrix, okay. And here the entry will be 0, 1, right. And you find that unlike in case of overlap, where both the min point and max points were changed, in this particular case I have the same hyperbox belonging to class 1, whose min point and max point will be the min point and max point of this particular neuron. However, that is not always the case, because I can have a situation where I will have partial containment. Okay. As we have already said that I can have a containment of this form. Suppose I have one hyperbox like this belonging to one class, and I can have another hyperbox like this which belongs to another class, okay, where this hyperbox is not fully contained within this hyperbox, it is partially contained, but still it is containment, because one of the dimension is contained in the respective dimension of the other hyperbox. Okay. So, to take care of such situations, I have to make entries in the V matrix in the W matrix to indicate that what will be the min point and max point of this particular neuron. Okay. And here the min point and max point of this neuron is nothing but the min point and max point of the neuron which is previously added. So, for that the min point max point was 0.45 and 0.5, right. So, I will have 0.45, 0.45 and here it is 0.5 and 0.5. Okay. So, you find that these two matrices V and W, they give you the min point and max point of all the hyperbox nodes in the middle layer, whether that node is in the classifying section or in the overlap compensation section or in the containment section. Okay. Matrix U gives you the information of the connectivity from the middle layer nodes to the output layer nodes in the classifying section. Matrix Y gives you the information about connectivity between the middle layer nodes to the output layer nodes in the overlap compensation section. And this matrix Z, that gives you the information of connectivity between the middle layer nodes and output layer nodes in the containment compensation section. Okay. And after this is done, what is required is that I have to combine the outputs of the corresponding classes. Okay. So, I have to combine the compensation output of class C 1 over here with the compensation output of class C 1 over here. Similarly, I have to combine the output of compensation neuron C 2 over here and the output of this. So, that gives you the overall compensation that has to be made. Okay. And finally, this is to be added to the membership function, which has been computed by the classifying neuron section. Okay. So, it comes over here. Similarly, over here I will have this. And so, final membership output I get from this point. Okay. So, these are the memberships which are the compensated membership functions of the sample to different classes. Okay. So, then what we said is, so in case of overlap, I want that if a sample is somewhere over here, that means it is near the min point and max point of one of the hyperbox. If this distance is greater than the distance of the same point from the min point and max point of the other class, okay, then its membership to the previous class should be more. Similarly, if the point is somewhere over here, which is nearer to min point and max point of this class than the min point and max point of this class, then the membership function of this point to this class has to be more. Okay. Similarly, in case of containment, if the point belongs inside, then its membership to this contained class has to be 1, its membership to the container class has to be 0. So, the membership functions of the compensation that has to be computed in case of overlap and the compensation that has to be computed in case of containment, they are different. Okay. So, accordingly the functions, the compensation values which are to be computed by the middle layer neurons in the overlap compensation section and the compensation values to be computed by the middle layer neurons in the containment compensation section, they will be different. Okay. So, how do they differ? If I take a neuron, input connections to the middle layers are given by these matrices V and W. It is the same matrix which is used for these connections, used for these connections, used for these connections. Because what I need over there is for this neuron what is the min point max point, for this neuron what is the min point max point, for each of these neurons what are the min points and max points. Okay. So, the inputs connections to all these neurons in the middle layer, whether it belongs to classifying section or it belongs to the compensation section, whether overlap compensation or containment compensation, all of them will come from the corresponding entries in the V matrix and W matrix. Okay. So, considering this, that the compensation that has to be given to different classes are different, compensation that has to be computed by the overlap compensation neurons and containment compensation neurons are different. So, the kind of compensation that we can compute is something like this. So, as we said that if I consider a neuron in the middle layer of the overlap compensation section. Okay. So, to compute this, what are the inputs that it needs? Obviously, it needs the information of the input vector A, because that only decide, I mean location of this A will tell you whether this is in the overlap section or it is not in the overlap section. Okay. It also needs the information of the min points and max points of the hyperboxes which are overlapped. That will be used to calculate the amount of compensation that we want to give. Okay? And it also needs the information of min point and max point of this node itself, because that will be used to check whether this point A is within the overlap region or it is not within the overlap region. Okay? And this neuron will give me two outputs corresponding to the two hyperboxes that has overlapped. Okay. So, I can put it like this: if this neuron in the overlap region, I represent this by say dj. Okay. So, this will give me two outputs, one corresponding to say djp and one corresponding to djq, indicating that the hyperboxes labeled as P and hyperboxes labeled as Q, they have overlapped. Okay. And accordingly, this output will be connected to the pth output layer neuron, and this output will be connected to the input of the qth output layer neuron. Okay. And the output function can be put like this: dj, let me put it as L, that will be is equal to u bj a v w minus 1, okay, into 1 minus minus 1 plus 1 upon n summation of max a I by w L I and V L I by A I. Where this summation will be I varying from 1 to n if I have n dimensional feature vectors, and this L can be P or Q. Okay. So, what does this expression give you? This B j A V W, okay, this V and W, these are min points and max points of this neuron. Okay, that is the compensation neuron. Okay. Whereas, this V L and W L, they are the min points and max points of the hyperboxes which have overlapped, right. So, this V and W, they are the min points and max points of the compensation neuron, whereas V L and W L, they are min points and max points of the hyperboxes which have overlapped. Okay. So, here you find that this function B j A V W, this is the same membership computation function of the classifying section neurons. So, there we have said that if a point falls within the hyperbox, then its membership function membership value will be equal to 1. Okay. So, this V and W, these being the min point and max point of the overlapped region. So, if a point falls within the overlapped region, then this B j A V W will be equal to 1. If it does not fall within the overlapped region, then the value of B j A V W will be less than 1, and its value will depend upon how far it is from that hyperbox. Okay. So, you find that if the point falls within the hyperbox, then B j A V w minus 1 is equal to 0. If it falls outside the hyperbox, the overlap region, in that case this value is negative. Okay. And if I use this u to be the unit step function. So, here what is u? U is the unit step function. So, if it is a unit step function, in that case u x will be is equal to 1 for x greater than or equal to 0, and this is equal to 0 for x less than 0. Okay. So, this clearly says that if the point falls within the hyperbox, then this b j a v w minus 1 is equal to 0 and the value of this function u will be equal to 1. Okay. If it falls outside the hyperbox, then this quantity is negative, it is less than 0. So, the value of u will be equal to 0, and if the value of u is equal to 0, then this entire product is equal to 0. So, there is no compensation. Okay. And if this u is 1, then the amount of computation depends upon what is the value computed over here. Okay. Now, here you find that the computation is 1 upon n into summation of max function a I by w L I. W L I is the ith component of the max point of W L. Similarly, V L I is the ith component of the min point of V L. Okay. So, forgetting about n dimensional feature vectors, if I consider only in one dimension. Okay. So, what effectively I will have is max A upon W and V upon A, or A upon W L, V L upon A, considering only one dimension. Okay. Here you find that if A and W L they are same, that means this unknown feature vector coincides with the max point, then this is equal to 1. Or if B and A they are also same, that is unknown feature vector coinciding with the mean point, they are same, then also this is 1. Okay. If unknown feature vector coincides with the max point, then obviously V L upon A will be less than 1. Okay. If unknown feature vector coincides with the mean point, then obviously A upon W L will be less than 1. Okay. So, here you find that if the unknown point coincides with either the mean point or max point, then this max operator will return you a value 1. Okay. And depending upon the distance of the point from the mean point or max point, this max operator will return a value whichever is maximum. And if you compute this value only between the mean point and max point of the same hyperbox, okay, then the kind of function that you are going to get is something like this. Suppose I have V over here and W over here of the same hyperbox, and depending upon the position of the point with respect to V and W, if it coincides with V or if it coincides with W, then the value returned by this max operator, that is equal to 1. Okay. As I move from V or as I move away from W, this value will go on reducing. Okay. So, I will have again after the midpoint, as it approaches V, the value will go on increasing. Okay. So, I will have a situation something like this, is not it? So, as we move away from W, the value goes on reducing, it will go on reducing up to say midpoint, then again it will go on increasing because of the influence of V. Okay. Similarly, over here if I have another hyperbox, so this is a V p W p, I have another hyperbox somewhere over here, it is a V q and W q which are overlapped. Okay. Here also the compensation values will vary in this form. So, you find that if the point is nearer to VQ, the compensation given by this is more. If it is nearer to WP, the compensation given by this is more.
Is it another hyperbox or dimension, another dimension?
This is another hyperbox. I am considering only in one dimension. I cannot draw multiple dimensions in a plane. Okay. So, this corresponds to one hyperbox belonging to pth class. This corresponds to another hyperbox belonging to qth class. Okay. So, you find that the compensation amount of compensation as computed by two hyperboxes, as computed by the hyperbox for different classes, they are different. Is it okay? And that is being subtracted from 1, right. So, wherever this component is more, minus 1, this will be less, where this component is less, minus 1, that will be more. I mean, the magnitude will be more. And then this, and obviously, this component will be either 0 or negative, is not it? Because this value can never be greater than 1. The maximum value is 1, it can be less than 1. So, this component is always negative. And this is this component that I am adding to the membership functions as calculated by the classifying section neurons. So, the final output, the maximum will be 1 if there is no compensation, or it will be less than 1 if there is compensation. And by how much less, that depends upon the relative position of the point within the overlapped region, whether it is nearer to the min point or max point of one class with respect to the other. Is that okay? So, as a result, within the overlapped region, what we get is somewhere over here the membership function computed to this class will be more, and somewhere over here the membership function computed to this class will be more. Okay. So, that is what is about the overlap compensation regions. Now, what about this containment compensation? As we said, the membership functions or the amount of compensation that you have to provide will be different from the amount of compensation that you provide in this case. Okay. So, here, so this is what is given by the, let us put it as OCN or overlap compensation neuron. Okay. Accordingly, I mark this as, so I will put it as CCN section or CLN section, classifying neuron section. This section is a overlap compensation section, and this is CCN, so containment compensation section. Okay. And as we said that unlike in case of overlap compensation section, where the output will be provided to neurons of two classes, in case of containment compensation, the output will be given to one of the class. Okay. So, accordingly, a schematic diagram of CCN, a containment compensation neuron, can be something like this. Again, it needs the input of the min points and max points, okay, and it has a single output, because the output will be going to only one output layer neuron. Okay. And if I put it as say neuron E, I call this as neuron say E j. Okay. So, the output of E j, I can put it like this, that this will be minus 1 into U B j A V W minus 1. So, this function is simpler than the functions to be computed by overlap compensation neurons. Okay. So, you find that here what does it compute? When an unknown point falls within the contained region. Okay. So, by contained region what I mean is either in this region in case of partial containment, if it is full containment in this region. Okay. And this V and W, they are the min points and max points of the contained hyperbox. That is, either it is the min point or max point of this, or it is the min point and max point of this in case of partial containment. Okay. So, again as before, if the point A falls within that contained region, okay, in that case B j A V W as before, this will be equal to 1, and this quantity B j A V W minus 1 will be equal to 0, right. If it falls outside this, then value of this will be equal to 0, indicating that there is no compensation. And if it falls within this, then what is the amount of compensation? Value of this function u, this is equal to 1 if it falls within the contained region, because then only this argument value is equal to 0. That means, the value of E j will be equal to minus 1. Okay. So, if the value of E j equal to minus 1 and this output is connected to the output layer neuron which contains the other hyperbox, right. So, in the classifying section neuron, the corresponding output node has computed a value of plus 1, this gives a compensation of minus 1. When you add these two, final value becomes equal to 0, right. However, this sort of containment compensation is not connected to, is not compensating the out of other classifying neurons. So, those values will be as they are computed. Okay. So, by using this, over here the membership function to class C 2 will be equal to 0, membership function to class C 1 will be is equal to 1, because this output is not connected to the output, is not compensating the output of C 1 classifying neuron. However, it is compensating the output of C 2 classifying neuron, and the amount of compensation is minus 1. So, this neuron has computed a value of plus 1, this has given a compensation of minus 1. So, final value becomes equal to 0. Okay. Whereas, for this one, this also has computed a value of plus 1, but there is no compensation. So, the final output will be, the final membership value will be equal to 1 to class C 1, right. Now, what happens if it falls in this region? The amount of compensation will be equal to 0. If the amount of compensation is 0, then the neurons in the classifying section, this neuron C 2, the neuron C 2 will give you a membership value of equal to 1. This neuron C 1 will give a membership function which is less than 1, and that depends upon the distance of this point from the min point or max point of this hyperbox, which is obviously less than 1, whereas the membership function computed by C 2 will be equal to 1. Okay. So, here I get a membership function where output of C 2 is 1, output of C 1 is less than 1. So, if I go for hard classification using these membership values, then obviously the point will be classified to class C 2, not to class C 1, whereas if it is within the contained region, the classification will be to class C 1 and not to class C 2. Okay. So, you can make this modification for improvement of this fuzzy min-max neural network, and this is what we are calling as reflex fuzzy min-max neural network. And it has been found experimentally that the performance of this reflex fuzzy min-max neural network is much better than the performance of the fuzzy min-max neural network as proposed by Simpson. Obvious reason is we are not going for any contraction, and as a result the error introduced while learning or training of the neural network is avoided. Okay. And then we will see later when we talk about the clustering that a further modification of this neural network can also be used for clustering operation. So, what we have discussed so far is classification operation. So, the next point that we will discuss is the clustering. Which makes use of the concept of unsupervised classification. Okay. So, what we have seen so far, we have said that those are supervised classification, because for designing the classifier or even for training the neural network, we use a set of samples for which the class belongingness are known, or the labeled samples. And using the labeled samples, you train the classifier or you train the neural network, and then use the trained classifier to classify the unknown samples. Okay. So, as you are training the classifier or you are designing the classifier using the labeled samples, so as if your training operation is supervised, you are supervising the training operation. So, that is why these are called supervised learning. Whereas, there is another kind of situation that we frequently come across, where given the raw set of data, we have to analyze the data, and based on some sort of similarity, we have to form clusters of data. So, it is something like this, that you have been given a set of data and you partition that set into a number of subsets, where the data of the vectors belonging to each partition will be similar based on some similarity measure. Whereas, if I take a vector from one partition and another vector from another partition, those two vectors will be different based on the same similarity measure. So, what we have to do is, we have to analyze the data, and based on the similarity measure, we have to partition the data into different subsets, and that is what is known as clustering. And because in this case we are not using any labeled sample for doing this clustering operation, so this is what is also known as unsupervised learning or unsupervised classification. Okay. And if time permits, later on we will see a hybrid approach, that we can have a mixture of supervised and unsupervised learning, because if your problem domain is very complicated, where you will have thousands and thousands of data for training of your classifier, it is not physically possible to label each and every training data for its class belongingness. So, you can have a small set or few samples of data from different classes, label them. Okay. Using that, you go for classification, and the unlabeled samples, because this will be similar to the labeled samples taken from the same class. So, the unlabeled samples can further refine your classifier. Okay. That is what is a hybrid approach, where both clustering and classification, or supervised and unsupervised learning approaches, they are used together. Okay. So, if time permits, we will discuss about that also, but next class onwards I will talk about the unsupervised classification or clustering. Okay. So, let us stop here today.